The Polymer Modification section of the Emerald model is designed for individuals with a solid background in polymer science and a strong understanding of the specific characteristics of the polymer that is being modified. If you don't feel comfortable modifying these polymers on your own, but your polymers do need to be tweaked for the purposes of your experiments, please give Mark Rule a call. He'll be happy to help you out. This page is intended to be used by resin companies and converters who are interested in developing new materials and new process conditions to explore what-if scenarios. That is, if a material with these characteristics could be created, what would the barrier performance be? And where the polymer properties in the material database need to be adjusted to more accurately reflect a particular polymer being evaluated. Now, I'm going to assume that you're an absolute genius in polymer science, and I'm going to show you how to use this thing. You'll note that on this window, you only have the option to modify an existing resin and not create a whole new one as you could in the Polymer Blend Creation tab. This makes sense because the intention here is to modify existing polymer compositions. Also note that you cannot modify polymer blends that contain composite materials here. To get started, choose the resin you wish to modify from the drop-down options. I'll choose PET 21% crystalline. You can adjust 8 separate parameters of your selected polymer. Ultimate orientation percentage. Fully strain hardened polymers possess 100% of their ultimate orientation, as extruded polymers are at 0% of their ultimate orientation. Intermediate levels of orientation can occur on stress relaxation from heat setting or when there is incomplete orientation. Adjusting the ultimate orientation percentage here allows you to assess the impact of orientation on your polymer's barrier properties. Crystallinity percentage. This feature allows you to assess the impact of polymer crystallinity on barrier performance. Changing crystallinity will also affect a polymer's modulus, which, in turn, will impact volume expansion and creep under pressure. This feature is useful for adjusting the crystallinity of polymers, especially those whose crystallinity varies greatly with process conditions. Cross-link density. All thermoplastic polymers have a cross-link density of nearly 0%. A fully cross-linked thermoset polymer can have cross-link densities approaching 100%. That is, every repeat unit is branched. This feature allows you to cross-link a polymer and examine the impact on barrier and gas sorption. The most frequent use of this feature would probably be for thermoset coatings. Oxygen scavenging capacity. With this feature, you can turn any polymer into an oxygen scavenger by giving it a non-zero oxygen scavenging capacity. Relative scavenger activity. This feature allows you to vary the activity of your oxygen scavenger over a wide range and examine the impact of scavenger activity on oxygen ingress. The nominal activity of 100% corresponds to a scavenging half-life of 2,000 seconds at 25 degrees Celsius and 21% oxygen concentration, with no diffusional resistance. The scavenger activity can be varied between 0 and 2,000%. Two uses for this feature are to establish the activity of a scavenger if the oxygen content versus time of a package is known, or to establish what the scavenger activity would need to be in order to have acceptable oxygen ingress characteristics. Hydrogen generation capacity. This feature allows you to convert a material into a hydrogen generator in the presence of moisture. This is used for modeling the high-guard oxygen scavenging technology. Relative hydrogen generation rate. You can modify the rate at which a material will react with moisture to generate hydrogen. Since the model already incorporates the effect of temperature and relative humidity on the reaction rate, changing this value only changes the pre-exponential term of the rate constant. The default is 0%. Finally, the catalyst concentration parameter allows you to specify the concentration of catalyst used for the reaction of hydrogen with oxygen. The default value is 0. Today, I am only going to adjust the crystallinity of the PET. Once you've made modifications to your polymer, give it a new name in the Save As field and click Save As. Now you should be able to make your own polymer blends using the Emerald Container Performance Model. Keep in mind that much of the information within these videos can be found in the tips links located at the top of each page.